What does the structure theorem for finitely generated modules over a principal ideal domain say when we take the PID to be the ring of integers? For this, recall that modules over the integers are just abelian groups. Indeed, if you have an abelian group, you can make sense of multiplication by any integer k. So if you have A is an abelian group and A is in A, and then for any integer k, you can talk about ka. This is equal to A plus A plus A plus A, k times if k is greater than 0, well, even if k is 0, and it's equal to A plus A plus A, let's say minus of, and then you take minus k times if k is less than 0. So you can define scalar multiplication by integers in any abelian group, and this makes an abelian group a Z module. And a Z module is again an abelian group, just the underlying abelian group of the Z module. So there's no difference really between abelian groups and Z modules. So let's see what the structure theorem says for Z modules. So if R is Z, then the structure theorem you get is a structure theorem for finitely generated abelian groups. Every finitely generated abelian group is isomorphic to a unique abelian group of the form Z mod d1z cross Z mod d2z cross Z mod drz cross Z to the power f, where d1 divides d2 divides dr, and all these di are positive integers, and we don't take them to be units, so we take them to be greater than 1. And of course f is any non-negative integer. So such a group is finite if and only if f is 0, and if, so let's call this A. So note 1, A is finite if and only if f is 0, and if f is 0, then the order of A is d1, d2, the product of these integers dr. You can ask, for example, how many finite abelian groups are there of order 12? Isomorphism classes of finite abelian groups of order 12. How do we solve this problem? So what we want is that A is going to be isomorphic to Z mod d1z cross Z mod d2z Z mod drz, and what we have is that d1 divides d2 divides dr, and of course d1 greater than 1, and the order 12 condition says that d1 d2 dr is equal to 12. If you think about this, you will see that there are only two possible solutions. The first is A is isomorphic to Z mod 2Z cross Z mod 6Z, and the second is that A is isomorphic to Z mod 12. Now, it's tempting to put in a third option. How about A is isomorphic to Z mod 2Z cross Z mod 2Z cross Z mod 3Z? Well, this is not a valid option under this rule because it does not satisfy this condition. D2 does not divide D3. And in fact, now you see the reason why we insist on these conditions for uniqueness. Because Z mod 2Z cross Z mod 3Z, this thing is isomorphic to Z mod 6Z under the Chinese remainder theorem. And so this third group here is nothing but the first group that we've written down. It's isomorphic to Z mod 2Z cross Z mod 6Z. So this, having this condition of divisibility is very important to ensure the uniqueness of the decomposition of finitely generated R module in general, but also for a finite abelian group. Now, if I were to ask you how many isomorphism classes of finite abelian groups of order 360 are there, this seems a little daunting at first because now you'd have to try to find all these numbers d1, d2 up to dr, which multiply to 360 and form a chain under divisibility. So there's a better way to do this, and this would use the primary decomposition. So recall that if you have an R module, then it's over a PID, then you define its P primary part as, let's say P is an element of R, that is P is prime. Then MP is defined to be those elements M in M such that P to the Km is 0 for some K greater than 0. So some power of P kills M, and M is said to be P primary if M is equal to MP, and also if M is a torsion module, then M is isomorphic to the sum over all prime ideals P of NP. So every R module can be written, every torsion R module can be written as a sum of its P primary parts. Now let's ask, when is cyclic R module P primary? So a cyclic R module is a module of the form R mod D. So R mod D is P primary. So we are fixing here a prime element P if and only if D is of the form P to the R for some, if the ideal generated by D is the ideal generator P to the R for some R greater than 0. R greater than or equal to 0 to allow D to be trivial. And the proof of it is rather simple. R mod D is P primary means that some power of P kills 1, the image of 1 in R mod D, which means that some power of P ends up inside D. So R mod D is P primary implies that 1 plus D into P to the R, P to the K belongs to D, is contained in D. Well, is equal to D for some K greater than 0, which means that P to the K belongs to D for some K greater than 0. Which means that D divides P to the K for some K greater than 0. But this is only possible if the ideal generated by D is the ideal generated by P to the R for some R greater than D. The converse is simple, and I will leave it as an exercise. As a consequence, suppose M is a finitely generated P primary R module. Then a priori we know that M is isomorphic to R mod D1 plus R mod dr. It's torsion because it's P primary, so there's no free part, there's no R to the power F. For some D1, D2, dr, D1 divides D2, so on. But because it's P primary, these things are just powers. We can say it's P to the R1 plus maybe P to the K1 plus P to the K1. And the divisibility condition says that K1 will be less than or equal to K2. Kr, where of course K1 has to be strictly positive. Now let's see what this says for abelian groups. So suppose A is a finitely generated abelian group. Then we have A is isomorphic to A torsion plus, and I'll write it in group notation, so I'll use the product here, product of groups cross Z to the power F for some F, and this A torsion is isomorphic to the product over all prime numbers P, AP, but since it's finitely generated, there'll only be finitely many primes in this, so maybe I'll write it this AP1 cross AP2 cross APT for finitely many prime numbers. For prime numbers, P1, P2, PT. Now let's ask how many possibilities are there for each of these. So A is P primary, a finite abelian group is a P primary Z module then we know that it is a product of groups of form Z mod P to the various powers of P. So this is the same as if and only if its order is a power of P. And so finite abelian P primary groups are the same as abelian P groups. So let's see, suppose A is a group of order 360 and A is abelian. Then what is the factorization of 360? Well, 360 is equal to let's see, 2 cubed into 3 squared into 5. So there are 3 primes occurring in its primary decomposition. So A is isomorphic to A2 cross A3 cross A5, and the order of A2 is 2 cubed, the order of A3 is 3 squared, and the order of A5 is 5. So now this A squared is going to be A2 is going to be isomorphic to Z mod 2 to the power K1 Z cross Z mod 2 to the power K2 Z and so on, where K1 plus K2, these things add up to 3 and K1 is less than or equal to K2 is less than. So the only way that you can have an increasing sequence of numbers add up to 3, the only possibilities are 1 plus 1 plus 1 for K1, K2, K3, or 1 plus 2, or just 3 itself. So there are 3 possibilities for A2, namely it can be Z mod 2Z cross Z mod 2Z cross Z mod 2Z, or it can be Z mod 2Z cross Z mod 4Z, or it can be Z mod 8Z. Similarly, A3 can be Z mod 3Z cross Z mod 3Z, or Z mod 9Z. A5, there's only one possibility. So totally there are 3 into 2 into 1 possibilities for A. So what we can conclude is that there are 3 into 2 into 1 is equal to 6 isomorphism classes of finite abelian groups of order, well, I don't have to say finite, abelian groups of order 3, 6. So let's put this calculation down in the most general terms. So if P is a prime, the number of isomorphism classes of abelian groups of order p to the power n is given by the number of sequences k1 less than or equal to k2 less than or equal to kr, and these have to be positive, such that k1 plus kr, these add up to n. So for example, and this lemma just follows directly from the structure theorem for finite abelian groups applied to P groups, because such a group is going to be of the form Z mod P to the K1 cross Z mod P to the K2 and so on, and this condition here ensures that the order of the group is P to the power n. So we'll make a definition. Let's say Pn, which is called the number of sequences like this, 0 less than k1 less than or equal to kr, such that k1 plus kr. These are called the integer partitions of the number of integer partition of this function n goes to Pn is a very famous function, and it was studied by Ramanujan, who found an asymptotic formula for it. And it remains a subject of considerable interest. So we still don't really have a good closed formula for computing Pn, although there are lots of analytic methods for doing so. So now for the final result, so the suppose n, maybe I'll write it as a theorem. Suppose n is a positive integer of the form p1 to the n1, p2 to the n2, pr to the nr is a positive integer, and this is the factorization into prime number. These are distinct primes, and these are positive integers. So for example, for 360 we had p1 is 2, n1 is 3, p2 is 3, n2 is 2, p3 is 5, n3 is 1. Then the number of isomorphism classes of abelian groups of order n is product j equals 1 to r p of n. And I guess the proof is clear by now. If a is equal to n, then a is equal to product j goes from 1 to r ap, where order of ap is p to the power n, apj, where order of apj is pj to the power ng. And then the number of possibilities for apj will be precisely p of nj. And these can be chosen independently. So the total number of possibilities for A will be the product of Pn, proving itself.